You ask a question and we have to conversation. We have gender biology, so he knows what.
What's the topic? Is it the same one as well? What's the answer? Look at the progress in the school. You don't want to go. What is it about?
Okay, I gave Justin. All right, guys, so this section you've seen, this is not totally new. And you're going to be doing the work. Let's see how much you remember. Okay, there's always one question of this. This is from algebra. Did I not give you one? Okay, I put it on a new meet on the. Am I not on the right one? For AP. I had changed the link so that I could record it. Are you on? Okay, just so that I could record it for decent. Okay, so cell phones away, right? Brains out. Remember what mathematical induction was? When I was in matric, which I know was a long time ago, mathematical induction was part of the core curriculum. All right, and every Friday we had mathematical induction question. Promise you got it wrong. Woo, you will be in trouble. And it was out of 10. They beat us up. Okay? Out of 10, and you had to get 10 out of 10. 9 wasn't good enough, and anything below 9, ooh. Okay? I had a very strict teacher. Okay? But she was one of the reasons that I taught, because she was just awesome, but you didn't mess with them. All right, so induction was in the core curriculum in those days. And then it got taken out and put in AP. Okay, but what is in mathematical induction? It's just a technique, a procedure of proving a mathematical statement correct for any natural number. So many of the statements are the patterns that you've seen, and it's proving that that statement is true for any natural number. And there's a technique to it. Now it's a proof. It's a formal proof. So you don't make up your own technique. Okay, there is a formal process in mathematical induction. You're proving a statement true. And there are 4 parts to it. First part is you prove it true for a natural number. So generally we prove it true for n equals 1. That is if the statement is true for all natural numbers. Sometimes you'll get a statement that says, this is a true statement for all natural numbers greater than or equal to 2. Then you wouldn't start at n equals 1. You would start at n equals 2. All right, so your first part is to prove the statement true for n equals 1. Your second part, you make an assumption. You say, let's prove it true for a natural number. Don't put that cell phone away. For a natural number between 1 and n, for some natural number between 1 and n. Let's assume that it's true for that. So we make an assumption. Then you prove it true for the next successive natural number, n equals k plus 1. And then that tells you that if it's true for n equals k, then it is true for n equals k plus 1. So if I have a natural number that it's true for, which is n equals 1, then it's true for n equals 2, n equals 3, n equals 4. It's true for every successive natural number. So your fourth part is your conclusion. All right, so I've written it all down for you in the booklet. It says prove the statement true for n equals 1. Assume the statement true for n equals k, and k is a natural number between 1 and n. Then you have to prove, the hardest part is 3. Prove the statement true for n equals k plus 1, the very next consecutive natural number. And then there's your conclusion. And the conclusion doesn't make up your own words. The conclusion you have to learn off by heart if necessary. If the statement is true for n equals k, then it is true for n equals k plus 1. However, it is true for n equals 1. We proved it. Therefore, by the principle of mathematical induction, it's true for n equals 2, 3, 4, i.e. all the natural numbers. So that little statement you have to learn. That's your conclusion. All right, we're going to do 4 now. The first two, you should recognize. Okay? We have done them, or Mrs. Richard did them with you last year. All right? And we will do the first one completely together. Then I'll give you time to do the second one. We'll mark it. Then we'll do the new type. And we'll do two of them. One relatively easy, one quite hard. And then we're done. Okay. So let's do this together. Right? And you need to listen. Right? You do the whole thing together. How to set it out. So in this first one, given that n is a natural number, proof by mathematical induction that this statement is true. And I put this one in, got a little bit of exponents in. All right, so the first thing, step one. All right, why don't I have a pen? What's happening? Good. Let's just see if it works here. Okay, let's just turn this off for a moment. Just hold on. Okay, you can start it. You put there, prove true for n equals 1. Prove true for n equals 1.
I know, but it's different. No. I don't know what to do with this. I've just put it with this.
Okay, I'll do it with you now. Just let me make sure. Let's see if the pen works now. Okay, guys, this is a problem. I'm just going to go out of everything. Just give me a minute. Who's on this group? All of you can stay. Okay, we're sharing so many buttons and okay, all right, we seem to be back on track. All right, so we're proving this statement true. Format is all about this. Okay, prove true for the first natural number, n equals 1. Okay? Right, now there are two sides to this statement. Are you listening? Because if you want your 14 marks or 12 marks for this, you've got to listen. They are giveaway marks. All right, your first term on the left-hand side is a third. That's when n is 1, when there's just one term. Your right-hand side, when n is 1, becomes a half into 1 minus 1 over 3. N is 1. You've lost me.
What do you mean?
First term. When n is 1, you've got one term only. Okay? There's your right-hand side. You let n be 1. All right. What is 1 minus a third? 2/3. And so what does the right-hand side give you? All right. Then you write there, left-hand side equals right-hand side. Therefore, the statement is true. For n equals 1. You proved it true for one natural number. That doesn't make the statement true for every natural number. It makes it true for one natural number. Okay. Part 2. Assume true for a natural number smaller than n. K. If you like, you can put there k is somewhere between 1 and, well, that's what it is, just so you know. Okay? 1 and n. You can put, can be 1 to n. Right? We're assuming it's true for a particular one. All right, now again, it's about how you set this out. So you're going to write 1/3 plus, this is my left-hand side, plus a third squared plus all the way down to, what is you letting n be? Okay, 1/3 to the k. That's the left-hand side. You're assuming it to be true is equal to, what does your right-hand side become? Half into 1 minus 1 over 3 to the k.
You can replace something.
Okay, that's assumed true for n equals k. That statement needs to be there. You can't do part 3 without that statement. So
ma'am, once we've done part 2, we can therefore say that 1 over 3 plus 1 over 3 squared plus 1 over 3 to the k equals. We still have to prove that they equal each other.
yeah, we're still going to prove that they equal each other. Okay. So now, all right, I'm not sure how I'm going to move this up because I'm working on a Word document. But anyway, I don't think it's going to let me. I might have to go down to another screen. Okay. So now you go to part 3. Now part 3 is where your marks come in. It's all about part 3. So I'm just going to go to my Word document. You're going to write it straight. Okay. Now you're going to go to prove true for n equals k plus 1. So I think with that k, you rather put it as 1 is less than k is less than n. K is somewhere, but don't put the equal signs because otherwise this isn't going to make sense.
Case the 1.
Okay? All right, now again, you're going to work left-hand side and right-hand side separately. And you're going to try and prove them equal to each other. The left-hand side is 1/3 plus 1/3 all squared plus. Now put in the second last term. That's 1/3 to the k, isn't it? And now you've added one more term, which is 1/3 to the k plus 1. You put everything down. This is where you guys take shortcuts. No shortcuts. This is a formal proof. All right. What is the right-hand side going to equal? It's a half into 1 minus 1 over 3 to the k plus 1. And you are trying to prove that this and this are the same thing. Using your assumption. So, using your assumption, what does that give me? What did you say in your assumption? This equals a half into 1 minus 1 over 3 to the k. Okay, that part. And what have I now got to add to it? 1 over 3 to the k plus 1. Now the trick is how we're going to get this to be the same as that. You're allowed to work with both sides. So let's stick to this side for the moment. Can we distribute this? Yes, okay. We're going to get a half minus a half times 3 to the k. What does this become? What's 1 to the k plus 1? 1. Over 3 to the k plus 1. Okay, do I want k plus 1s there? I do. But more importantly, I want to be able to simplify this. So what is 1 over 3 to the k plus 1? What can I do to the denominator? Okay, split it up to 1 over 3 times 1 over 3 to the k. So it's all your rules for exponents from core maths you need to be able to do. Now, are these like terms now?
Yeah.
Are they like terms? Minus a half times 1 over 3 to the k plus a third. You don't have to put this line in, but are they like terms?
Yeah.
Minus a half of something plus a third of something gives you what? What's minus a half plus a third? Common denominator of? Minus 3 plus 2. It's going to give you minus a sixth, isn't it? Yeah? Half minus 1 over 6 times 3 to the k. Okay, 2 steps back.
1 over 3 times 3 to the k.
1 over 3, this one.
How do you get that?
Okay, this one would have given you 1 over 3 to the k plus 1, and I split the indices.
Yeah, you split 1 over 3, 1 over 1 to the k plus 1.
Well, it is. What's 1 to anything? What's 1 to the k plus 1? Okay. All right. So now you can choose to fiddle with that, or do you want to continue here? You can. You're allowed to, but I'm going to carry on here. But I'll do both ways. All right? Can I split this up? Take out a half, and you're left with 1 minus 1 over 3 times 3 to the k. And isn't that what we wanted? So your knowledge of exponents is going to be crucial here. No messing up exponents. Here, from there to there. 1 above. Okay, what's minus a half of something? Minus a half of something plus a third of something. Aren't they like terms? Common denominator of 6 minus 3a plus 2a is minus 1a over 6.
Wait, can we just copy down the conclusion?
No, not yet, not yet.
What?
Not finished.
You have to say left-hand side
Okay.
equals right-hand side.
All right. Are you happy with having continued?
Yes.
If you're not, just for a moment before we finish it off. If it's not, you could have gone to this side. Distributed that. Distribute this. You get 1 over 2 minus 1 over 2 times by 3 to the k times 3. Would that give you a half minus 1 over 6 times 3 to the k? Would you have been able to go to that?
Yep.
Are you allowed to work with both?
Yep.
Yes. As long as you don't put them equal to each other. The number of students, if you put them equal from the top, then stop, because why are you proving them equal if you're saying they're equal?
Oh, exactly.
Exactly. And you'll get naught for that part. Okay, so don't put them equal if you haven't proved them equal. Okay, so how do you finish this off? You say left-hand side equals right-hand side. Therefore, the statement is true for n equals k plus 1. And what's your fourth thing that you write? The conclusion. Do you understand what the conclusion is saying? Not really. Okay, so think about it. You're saying if it's true for n equals k, then it's true for the very next number. Isn't that what that's saying? Okay, so as long as you've got one number that it's true for the very next number. So do we have a number that it's true for? N equals 1. Isn't that our k? So is it true for n equals 2? Then our k becomes n equals 2. Then is it true for n equals 3? Then your k is 3. Then it's true for n equals 4. So then it's the domino effect. If it's true for one, it's true for all of them because you've got that first number it's true for. And where do you get that from? Your assumption. Your assumption said if you can find one number it's true for, then it's true for the next number. So have you found that one number it's true for? Yes, n equals 1. So then it's true for 2. Once you know it's true for 2, then it's true for 3. Once you know it's true for 3, it's true for 4, etc. That's the domino effect. You just need one it's true for because your assumption and the proof prove that if you've got one it's true for, it's true for the next consecutive natural number. So it's dealing with consecutive natural numbers, and that's the principle of mathematical induction. That makes sense. So the conclusion goes, if it's true for n equals k, then it's true for n equals k plus 1. But it is true for n equals 1, therefore it's true for n equals 2, 3, 4, 5, 6, i.e. all the natural numbers. By the principle of mathematical induction, not by the principle of dominoes, by the principle of
How
mathematical.
many marks are the conclusion part?
2? You can't just write conclusion. Okay, so now there's one for you to try on your own, and you've got 10 minutes max, okay, for you to try on your own. No, prove true for n equals 1 or p equals 1. No, it's not in because what have you got to always do with the sigma problem? No. What my class? What have I always told you to do with sigma?
Break it up.
Expand it, get the pattern.
Yeah.
So n, you're still going to have in terms of n. How many terms are there in this pattern? So what's your first term? Get your pattern.
But it says t equals 1.
Yeah.
So then you just gonna
Okay, we need to all be on the same page. We're going to try this one on your own. But it's a sigma problem. Sigma patterns. You get what you look and see what expanded. So do that first. Expand your patterns. You do know how to do it. Okay, but expand the pattern first before you do anything. So we're not going through 1, 2, 3. Get me the pattern. Everyone. No, there are 4 to do. We've got 3 to go.
if you don't get a half year wrong.
No, there's no P's in the pattern. There not. No, no. Expand the pattern, and if you've got a P left in that pattern, you've done it wrong. What is the first term? When P is 1, it tells you. Start. So the first term is 1 over 1 times 2. Sigma. Sum of all the terms. Come guys, you've done sequences and series. What is the next term? 1 over
6.
2 times 3. Don't multiply out. What's the next term? 3 times 4 plus. What's your last term? What's your last value of P?
1 over
N. So it's N into?
N plus 1.
Right, where's the P's left in this?
1.
They're gone. Okay, and what are you trying to prove that the sum is equal to? That's now what that's the mathematical statement you are trying to prove using mathematical induction. So you make a note to yourself. If there's a sigma problem, expand it. Get the pattern. Okay, now I do just step 1, 2, and 3, and then you can write conclusion.
Okay.
No, you must write out everything, like assume n is equal to k, etc., etc.
Yeah, it's a formal proof.
But man, do you actually see the different numbers? Yeah.
Yeah, it's a sum. Sigma means sum of. Sigma means sum of.
You say.
No, it's
Nothing.
Yeah?
Is it okay for the third step would be
Oh,
like when you go k plus 1, because it's already k plus 1, can you just make it k plus 2? Yeah.
yeah.
You plus them together and give me cancel. This one,
Thomas, you must put your mouse.
that's maybe.
1%.
That's
We got k to k plus 2 is equal to k to k.
good factor. Yeah,
Okay, tell me when we can mark it.
2 minutes left.
2 minutes.
Once you're out, you'll see the k plus 1.
And you want to go.
I don't know what I did.
Something we did it. Okay.
You know, you can do it now, and then you're gonna come to the test. Oh, yeah. There's some other curveball actually.
But it's not always be a curveball, but it don't, as long as you stick to, you can get marks from just knowing the actual format of the proof and not taking shortcuts. Remember, it's a formal proof, so no shortcuts.
You have to write conclusion.
Yeah, then you can just write the conclusion. We're not going to write the conclusion 4 times today. But you can write it out. If you write it out now, you'll at least learn it.
Man, do you plus your last thing to your.
Yes, you add it.
Oh, okay, that.
Not to the right-hand side. The right-hand side must just become k plus 1 over, yeah, the right-hand side.
What are you adding there?
No, you're letting k be n be k plus 1. So it's going to be k plus 1 over k plus 1 plus 1.
Yeah. So I've got that. Then what do you plus that?
Nothing. That is the right-hand side. This is saying that the sum of all these terms will always be equivalent to that.
Yeah.
So if you're adding 10 terms, it's going to be 10 over 11. If you're adding 30 terms, it's going to be 30 over 31 of this pattern.
So then you just take the last, your 1 over k plus 1 plus 1. And then what do you do from there?
Okay, well, I'm going to do it now.
That's it.
The composition, like the very last one, it says,
Because you
should
have
add
to
numbers
n. No, so that's your first one.
All natural numbers are the natural, little h. All natural numbers.
Yeah, so that's it.
All
When you
natural
go to
numbers,
that bit.
you can also write that.
So once you've got 1 over k, it's k plus 2. Huh? Wait, yeah, you still.
So it's true for all natural numbers.
Just
Yes, that's more. Okay, let's do it. Guys, can we? All right, prove true for n equals 1. Means you're only counting one term. You're only counting this term. So what is your left-hand side? Half. What is your right-hand side? It's going to be n is 1. 1 over 1 plus 1 is a half. Did you put left-hand side equals right-hand side? Statement is true for n equals 1. And you probably got yourself a mark or two. Set up like that. All right, now we assume true. So you're going to write 1 over 1 times 2 plus 1 over 2 times 3 plus all the way down to 1 over k into k plus 1. You're letting n be k. You're assuming that the sum of all those terms equals k over k plus 1.
Yeah.
You're making that as an assumption. And k is some number between 1 and n. It is a number smaller, somewhere in that pattern. We proved it true for 1, it's less than n. Happy with that?
Yeah.
Now we're going to, with our assumption, we're going to prove it true for the very next consecutive natural number, n equals k plus 1. So we have a left-hand side. Your left-hand side is 1 over 1 times 2 plus 1 over 2 times 3 plus. Now we include this term, the second last term. We include it. And then we add one more term. One way n is k plus 1. So what does it become? K plus 1 into k plus 2. That is your k plus 1 term. Okay? What is your right-hand side that you are trying to prove it equal to? What does your right-hand side become when n equals k plus 1? K plus 1 over k plus 2. And we're trying to prove that statement is equal to this. You split your page in half. They're not equal yet.
So remember, this is the last like was the k plus 1 plus k plus 2.
This one, okay? Remember?
Under that.
This one.
Yeah.
Okay, remember that's what it was. So what are you putting in place of k? In place of n? Okay, all right. All right, what did we assume that was? My curly bracket didn't work so well. What did we assume that was all equal to? This is equal to k over k plus 1 from my assumption. That is that, it equals that. And now I've got to add it to that. And how do we add fractions? And what is your common denominator? K plus 1 into k plus 2. Right, this goes into here. K plus 2 times. Doesn't it? And this goes into here once. So we're left with k squared plus 2k plus 1. Little bit of grade 10 and 9 algebra. Keep that there. How am I going to get that to equal that? What must I do to the numerator? Factorize. And what does it factorize to? Excellent. Could you have guessed that? Should have. Okay, k plus 1's cancel, and do I get them equal to each other? All right. So the left-hand side equals the right-hand side. Therefore, the statement, you're right. Therefore, the statement is true for n equals k plus 1. Did you get that?
Yeah.
So that's a nice, easy one. Therefore, the statement is true for n equals k plus 1. And then you write your conclusion. It's cell phone right next to the screen, so she doesn't know, but she knows. Okay, yeah, I know. I promise you, that's one thing I do know what happens in my class. It's either in the pencil bag, or it's next to the screen, or it's another pocket by the chair. Okay, right. In your textbook, there's a number of these, some of which you did last year. So now we're going to add a degree of difficulty to these and just do divisibility kind. So if you look at example 3, it says, there's a mathematical statement. Prove that 3 to the 2n minus 1 is divisible by 8 for all positive integer values n. All positive integer values n. So that's n equals 1, 2, 3, 4. All your natural numbers. Prove that that statement is true for all positive integers of n using mathematical induction. Right. So, no trial and error. This is our statement. And we have to prove that it is divisible by 8. So what do we do first? Prove true for. Let's see if the statement is true for the first, for one of our first natural numbers. So, can you do that?
I don't know what the left-hand side is.
There's no left-hand side. The statement is that 3 to the 2n minus 1 is always divisible by 8. So if you let n be 1, is it divisible by 8?
Yes.
Well, you're going to get 3 to the 2 minus 1, right? So 9 minus 1, which is equal to 8. Right? Which is divisible by 8. Have you proved it true?
No.
So it's true for n equals 1. There's no right hand side. The statement has to be true. Is it true for that for n equals 1?
No.
Okay. Now what do we do? Assume true for n equals k. The k is between 1 and n. Assume true. So we're going to do it in red. Okay, that tells us that 3 to the 2k minus 1, we're assuming it true, is going to be 8 times by something. Okay, 8 times by p, let's say. And p is some integer. We're assuming it's divisible by 8. It means you can take out a common factor of 8. It's an assumption. 8 times by something. Okay, leave a bit of space there. We're going to have to write some more there. It's an assumption. Assume true for that. Okay. Now we're going to prove true for the very next natural number. Using our assumption. Okay, remember we used our assumption before, we're going to do the same now. Okay, so let's get what our statement is. It becomes 3 to the
2k plus 1.
2k plus 1 minus 1 is my statement. I'm going to fiddle with this. Try somehow to use the assumption to help us. Okay. Have to know your rules of exponents. So let's multiply this out. 3 to the 2k plus 2. What am I going to have to do to that in order to use my assumption? Split it. Okay, I didn't have 3 to the 2k plus 2. But I had 3 to the 2k. Can I get that somehow out of this? Splitting. 3 to the 2k times 3 to the 2. Okay. Now, can you replace this? Well, what will it equal? It will equal 8p plus 1 from my assumption.
1 plus 1.
Well, make that the subject of the formula. Okay, so this can be replaced with 8p plus 1, and it's times by 9. Minus 1. Okay? So, I'm not going to multiply the 9 by the 8 because I want it to be divisible by 8. I want everything to have an 8 in it. So, I'm going to leave it as 9 times 8 times p plus a 9 minus a 1. So, all I've done is distributed that. Okay? So, now I've got 9 times 8p. What does this give me? Plus 8.
Oh, 9 times 8.
Well, 72, you can still take out an 8. Can I take out a common 8?
Yes.
And what am I left with?
9p plus 1.
And is it divisible by 8?
Yes.
Which is, you're guessing. There's the 8. 8 is a factor, which is divisible by 8. Just do one. What? Very nice.
They ask this question in the test.
Okay. And then what do you write? What's next? What's part 4? Conclusion. Okay. If it's true for n equals k, which we assume, then it's true for the next natural number, which we proved. But we didn't find it natural number 1, where it's true, so therefore it's true for 2, 3, 4, 5. Okay. One more to go. Started. This is a hard one. It's asked. I want to say it was asked in like 2010. So 10 years later, maybe they're wanting to ask it again. But there's a typo. Typo. That must have a plus sign. It must be x to the 2n minus 1 plus y to the 2n minus 1. Makes it much easier. Much easier. Okay? So we all fix the typo. Okay? It's a plus sign between the two. That's a plus sign. Okay? It's x to the 2n minus 1 plus y to the 2n minus 1 is divisible by x plus y for all natural numbers n. I want you to do part 1 first. Prove it true for n equals 1. So this one you're going to put a star next to it. This one is hard. Did you do the first part? Okay, all right, you let x be, you let n be, so it's 2 to the 1 minus 1 plus y to the 2 to the 1 minus 1, and you get x plus y. Is that divisible by x plus y? Okay, which is
1.
divisible by x plus y. So it's true for n equals 1. Okay, write out your assumption. Assume true for n equals k, so k is between 1 and n. Right, very important line. Okay, we're going to have to assume that it's divisible by x plus y. So you're going to get x to the, what was it? 2k minus 1 plus y to the 2k minus 1 is divisible. Means it's got x plus y as a factor. So you can write x plus y times by something. Oh, do you want to stick to p? P, okay. So p is some integer. Okay, leave a space there. We're going to have to fiddle with that. Right. Leave a space there. True. True. 4 n equals k plus 1. I hear some of you saying separate, so that's good. Let's keep our assumption handy. Let's just stick to back here. All right. How are we going to use that assumption? How are we going to use that assumption? Okay, so you're going to get x to the 2 into k plus 1 minus 1 plus y into 2 into k plus 1 minus 1. Now you can multiply those out and you're going to get x to the 2k plus 1, aren't you? But we've only got something about x to the 2k minus 1. So be a little bit sharp here. If you multiply this out, you're going to get 2k plus 2 minus 1.
Yeah.
So do some splitting here. We want the 2k minus 1. That's telling me I want the 2k minus 1. So what am I left with? A plus 2, aren't I? Okay. Look at what you've got here. You've got x to the 2k plus 2 minus 1.
Yeah.
All right, this is the problem one.
Oh, I see.
I want the 2k minus 1. So split your indices there. Can I split it? Let's do it in blue. To x squared times x to the 2k minus 1. Will that give me the same thing? How do I know to do that? Well, I want the 2k minus 1. I don't want the 2 there. So I split that one away. So it's this one that I split away.
Yeah.
Okay? I'm going to do the same with the y. So what are you going to get? Y squared times y to the 2k minus 1.
No, I'm not saying I'm getting the last one.
Okay? If you multiply this out, John, you're going to get x to the 2k plus 2 minus 1, which is x to the 2k plus 1. Okay. I don't want x to the 2k plus 1. I know nothing about it. So I want to rewrite this. I want to take the 2k minus 1, and the plus 2 is the problem. So when do you add indices? What have you done to your powers to add the indices, or powers with the same base? You've multiplied powers with the same base to add indices. So can I not split this? Keep the 2k minus 1, but write that as x squared. So I'm undoing that operation of multiplying powers where you add the indices. And how do I know this is guiding? This is up here. You've got to be guided by your assumption. Okay, so now, if I want to replace this with something, can I make x to the 2k minus 1 my subject of the formula here? What will it become? P into x plus y, just because that's a meter, minus y to the 2k minus 1. By making that the subject, it becomes this minus that, doesn't it? All right. Can I replace my square with that?
Yeah, I guess.
No, not can I or can't I? Okay, right. So let's replace it. P into x plus y minus y to the 2k minus 1 plus y squared times y to the 2k minus 1. Told you it was a bit harder.
But then you can take out.
Only x to the 2k minus 1 that equals p to x plus y.
Yes. Isn't
Not y.
No, because I didn't make y the
Check
same.
one and the other.
You know what? You want to have like terms, and I'm not going to have like terms here. I only replaced one of them. You can't replace both. I only made that one the subject. If you only wanted to make this one the subject, that's also fine. You can make one or the other, but you're not going to make both.
Can't you take out from when you have 2x into 2k minus y times x squared plus 2k minus y times y squared? Can't you just take out can't you just split that?
How?
And then you have like a 2k minus 1 plus 2k plus y into 2k.
There's no common factors here. You can't factorize this. Nothing's common. Be careful of that. Okay. All right. Do I distribute now? Okay, let's distribute. X squared times p into x plus y minus x squared times y to the 2k minus 1 plus y squared times y to the 2k minus 1. Now this has already got an x plus y in it. I wouldn't touch it. Wouldn't we prove that that term's already? Okay, it's these two. Are these two like terms, or they have something in common? I think they've got y to the 2k minus 1 in common. Okay, let's take it out. Okay, I'm going to take, what must I take out? Plus y to the 2k minus 1 or minus y to the 2k minus 1? No, minus, okay? And what am I left with?
Explain minus y.
And can that factorize? To what? See why you did grade 9? Dots, and what's it called? Difference of two squares. Okay, is there a common factor that I'm looking for? No.
X plus y.
Isn't this common? Okay, so x plus y into x squared p minus y to the 2k minus 1 into x minus y. Which is divisible by x plus y. If it's true for n equals k plus 1, therefore conclusion.
Can't be done the syllabus.
This is recorded.
Can you please put
Okay, the other wasn't recorded. It wasn't allowing me to. But induction is recorded. Okay. All right. There are a number of these that you need to do. Just let me finish, please. There are a number of these that you need to please do out of your grade 12 textbook. If you come across one you can't do them off past papers. Sometimes they give you part and they only ask you to do part 3. So there are different ways of asking induction. Okay, bottom line is we're done with the curriculum. On Friday we're starting at 11 o'clock. Right, and we're going to go till 2 o'clock doing just integration. Looking at all different tabs and trying to match this is this tab, that, just so that will help you to put them in compartments and to recognize them.
Is it serious?
Well, let's see how, it goes.
Now, what time is school tomorrow?
What time is school tomorrow?
I'm actually going from like the 9
Opposite after 12, counting minutes tomorrow. Let's just see how we go. Remember, not too much, you like the worksheet. But it's a really good. But you're not allowed to use combinations. Not allowed to use it. We don't talk about combinations. We do to practice. We go back to basics. I will not use the word combination. Go back to basics. Thanks guys very much. Thanks. That's what I'm going to ask you a big favor. You also said that if Mr. Rogers is here, that we can see what we're back. Otherwise you're taking them to you.
Oh,
Well, then you can check what you have.
no.
You're not going to have. Wait, you Have you not been in a study before? Okay. Thank you very much, all of you. We managed, we got through it. Wasn't so bad.
No.
18.
I asked to drop 80 in the first week of grade 8, and I actually managed to do it.
In grade 8. You never had it in grade 8.
After the first lesson, because I missed the year of 80
Yeah.
Who was he?
So,
One before the IT.
yeah, or yes, so that other one. But otherwise, just keep them in your for your house.